Hello everyone, hope you're doing well. I'm Rukaiya ma'am. So the topic which we are gonna discuss today, that is gravitation from class 9. So I think we all have experience. Suppose we have a pen in our hand and when we drop that pen, so it goes straight down to the floor, or we can say to the earth surface, right? Or suppose we have a ball in our hand and we are throwing that ball in the upward direction. So it reaches to a certain height, then again it goes down to the floor or the earth surface, right? Or even us, we are standing on the earth surface. So that means earth is pulling all of this and even us in towards its center. So there's this attraction between earth and all of this object. So this kind of pull or attraction is known as gravitational pull. Okay, so this is gravitational pull that act towards earth and all of the object. Now it's not about there is some attraction between earth and all other objects. There is some attraction between the pen and me. There is some attraction between between me and the pen, or there is some attraction between the pen and the ball. So each and every object attracts every other object towards them. But the fact, like suppose I have a pen in my hand, but that pen is not attracted towards me. Like we can't see that, right? Or I am not falling towards the pen. Or not any other object at your room or at your house is moving around because of the attraction of each and every object towards them. So basically, the gravitation between the earth and every other object is way more larger that we can't feel these attraction between me and the pen or the pen and the other object. Okay. Then again, we can see that moon is rotating around the earth. Then planet like earth, planet, or all of the planets are rotating around the sun, right? So if earth is attracting all of this like every other object or earth, so that means earth can attract moon as well. So there might a chance that earth can like the moon is falling on the earth surface, but that doesn't happen, right? Moon rotates around its own orbit. So basically what happens here, suppose this is our suppose this is our moon and this is our earth. So moon is rotating around earth in this manner. So whenever that moon is rotating around this earth, so each and every moment there is this change in velocity on moon of moon. Okay, so this kind of velocity is known as tangential velocity. So we can understand this tangential velocity with some kind of simple activity that we can do at our home. Suppose you have taken a string and at one end of that string you have tied a stone, and at the other end of the string you are holding that string and you are whirling it around. Okay, so whenever whirling it around, you will see that stone is changing its direction, like the velocity of direction is changing each and every moment. And if we release that thread, you will see that the stone is going straight along the tangent. Okay, so your hand is basically responsible for your hand is giving that kind of force to that stone so that it can move in a continuous circular orbit. So here also, like there is some kind of forces acting towards the moon and the moon and the earth, and that force is basically center seeking force. So we can see that each and every moment moon is rotating around the center of the earth. So this kind of center seeking force is acting, center seeking force, and that center seeking force is called as centripetal force. And this centripetal force is provided by gravitational force. Okay, so the gravitational force is very much responsible for the rotation of the moon towards the or like the earth. Okay. Gravitation is like it's a force that holds the universe together, and every object in the universe attract every other object with an invisible force called gravitation. Now gravity gives us weight, it gives us like it keeps the moon orbiting earth, create ocean tides, then ensure planets stay in their paths around the sun. So with the same logic we can explain like how planets can move around the sun as well. And without gravity the universe as we know it wouldn't exist, because obviously if there is no gravitational force, so all of the object will collapse each other and there will be no life exist on the earth. So this theory was given by a famous scientist called Sir Isaac Newton. So you all know the story, the apple falling story basically, but let me say that story in a brief manner. So one day Sir Isaac Newton was sitting under a tree and the apple fell on him. So when that apple fell on him, the first thing came to his mind that why that apple is falling in the downward direction, why it's not going in the up, and why earth is attracting that apple, and if the earth attracts an apple, can it not attract the moon? So this kind of question came to his mind, and then later he gave us his famous law, which is the universal law of gravitation, which is known as Newton's universal law of gravitation. And according to him, the gravitational force is directly proportional to the product of the masses of the two objects and inversely proportional to the distance, square of the distance. Okay, so basically let's imagine that these are the two objects, and let's say the mass of mass of this object is capital M and the mass of this small object is small m. So the distance between these two objects is, let's say this is small d. Okay, so according to Newton, he says that gravitational force is directly proportional to the mass of the two objects, so m into m, and gravitational force is inversely proportional to square of the distance. So when we merge these two equations, we'll be getting, so F is proportional to m into m divided by d square. So when we remove that proportional, we'll have a constant. So F is equal to GM1M by d square. Now this G is basically the constant here, and this constant is very, very important. So G is known as universal gravitational constant. And the numerical value of this gravitational constant was given by a scientist called Henry Cavendish, and he did this experiment like torsion balance experiment, and from that experiment he gave this value 6.67 into 10 to the power minus 11 Newton meter square divided by kg square. So this value is constant. Okay, like wherever you go, this value remains constant. So that's why we are using this universal gravitational constant term. Okay, so this is given by Henry Cavendish. Okay, see here we have one question, and it says, what is the magnitude of gravitational force between the earth and a 1 kg object on its surface? Mass of the earth is given, that is 6 into 10 to the power 24 kg, and radius of the earth is given, that is 6.4 into 10 to the power 6 meter. Okay, now generally whenever this type of question comes to your exam, first of all you must remember the numerical value of the gravitational constant, which is 6.67 into 10 to the power minus 11 Newton meter square per kg square. Okay, now here the given letters we can say that the mass of the earth is given, so capital M, which is the mass of the earth we are taking, so this is 6 into 10 to the power 24 kg. Small m is 1 kg only. So we can see all of these units are in kg, that means in SI. So the radius of Earth is given, so we can take radius as r. So r is 6.4 into 10 to the power 6 meter. So here also the radius is in meter, so that means all of these are in SI unit. Now one more thing, that since gravitational force is also force, so the SI unit of gravitational force is also in Newton. Okay, so this Newton is came after the scientist name. So we know that F is equal to Gm small m divided by d square. So here we are taking the radius of the Earth, so this is r square. Okay, so this is equal to 6.67. Now we are substituting all the values here. So 6 into 10 to the power 24 kg into 1 divided by r is 6.4 into 10 to the power 6 meter square. And if you calculate these values, like after substituting all the values, if you calculate them, then you will get the value of force, gravitational force is 9.8 Newton. I have done the question previously, so I can tell this is the correct answer. So that much of amount or magnitude of the gravitational force between the Earth and the 1 kg of object can like this is the magnitude basically. So this is our answer. This same theory or concept, that what happens to the force between two objects if the mass of one object is doubled. The second one is the distance between the object is doubled and tripled, and the masses of both objects are doubled. Now this is a very good, like it's an important question. It's, and this type of question can come to your exam as well. So we know that F is equal to GMM by r square. Okay, now it says when, in the first question we have when the mass of one object is double. So that we can take any of the mass. So let me take that capital M is now double. So the new mass is basically, let's say M dashed is equal to 2m. Now we have to substitute this M dashed in our equation. So now F dashed would be, so this is our new force, which is G2M m divided by r square. So GMM by r square gives us F. Now this time we're getting an extra 2. So this would be 2F. So that means the new force is basically double of the previous one. So whenever mass of one object is double, the force gets double as well. Okay. Next one is when the distance between the object is doubled and tripled. So let's say that now r dashed is 2r. And let's say r2 is 3r. So first we're using this r dashed. So F, let's say F1 is equal to, so GMM divided by, now this time r square is not r square, it's r dashed square. So the value would be GMM by 2r square. So this would be 1 by 4 GMM by r square. That means the new force F1 would be 1/4 of the previous force, which is F. That means when the distance gets doubled, the force gets 1/4 of the previous one. Now let's say F2, that means when R2 is 3R, that means the distance gets tripled. So let me take the equation. So this is R2 square. So GMM by 3R square. So this time it is 1 by 9 of GMM by r square. So 1 by 9 of the previous force. So whenever the distance gets tripled, the force is 1 by 9th of the previous force or the first force. And in the last we have when the masses of both objects are double. So this time M dashed is already 2m. Now small m is also doubled, so we can say M dash is equal to 2m. Now this time the force is, let's say F3, so this would be G M dash small m dash divided by r square. So G 2m small 2m divided by r square. So this would be 4 of GMM by r square. So this would be 4 of F. That means when the masses of both objects are double, that time the force would be like fourth of the previous one. That means it's get quadrupled basically. Okay, so that's it. Like in this session we have discussed about gravitational force, the Newton's law of gravitation, then we have done two numericals from NCERT which are very important, so you can solve this kind of questions from your book also. So that's it for today. Hope to see you soon. Bye everyone.